in the former Soviet Union, and then he studied and he was also a professor at the University of Moscow.
No, I was not.
Just
Academy of Sciences.
Academy of Sciences.
Institute for Oceanology.
Oh, sorry. Sorry for that. In Moscow. In 1991, he moved to Tel Aviv, where he's now a professor at Tel Aviv University. He has worked in several fields, including dynamics of solitons and vortices, as well as weakly nonlinear approximation for pattern formation and these sort of things. He has published many papers, hundreds of papers, and just to mention one, he has a nice review on solitons in nearly integrable systems, published together with a Yuri teacher that at this point has about 800 citations. As of today, it has 796 citations, which is good. Professor Malomed is now visiting at IFISC for the period of time. He's staying there on a sabbatical. And since IFISC is nearby here, we took the opportunity to invite him to visit us, and he's going to stay with us until Friday. So he's upstairs. If you want to talk with him on any topic of what he's going to talk today, or other topics that he has worked in, or linear dynamics of solitons or whatever, please feel free to contact me and we can arrange the schedule to talk with you.
Okay. Thank you very much, Pere. So I would like to thank Pere and also Daniel Gomila for the invitation to come here. It's my second chance to visit this university. I once visited it being invited by Max Samliger, but it was very long ago, definitely more than 10 years ago. So it was another very nice chance to come here. And as already Pere mentioned, my current university is at IFISC near Barcelona, but it's just for 8 months of partial sabbatical. My permanent address is the Department of Physical Electronics, which is a part of the Faculty of Engineering at the Tel Aviv University. Okay, so let's proceed to the topic of this talk. So I will try to give a short overview of some results, chiefly theoretical, but also some experimental results will be mentioned, which have been accumulated in principle in the course of the last 20 years, or even a little bit more, but many of these results were obtained relatively recently, let's say in the course of the last 10 years. And all these results, which I'm going to briefly overview in this talk, they were obtained in physical systems which were built as dual core systems, so that what one has in this case, this is a system of two parallel waveguides for some waves, which may be optical waves or maybe matter waves, in the case of Bos Einstein condensation. And the typical situation is that because of the intrinsic nonlinearity in each waveguide, each waveguiding core is a system with some intrinsic nonlinearity, and they are separated by the two parallel cores, two identical cores are separated by some effective barrier, and these waves, photons, or maybe coherent atoms in the case of BEC, they can tunnel across the barrier which separates the two waveguiding cores, so that the first approximation, this coupling between the cores is linear. And overall, we have the interplay of the intrinsic nonlinearity in each core and the linear coupling between them. So this type of systems has many particular realizations and applications in several areas of physics. And the subject of this talk is to briefly review basic types of stationary states or eigenstates which one can expect to find in such dual core nonlinear system. So first of all, of course, if we are talking about linear dual core systems, the most well-known example would be just a double well potential in traditional one-dimensional quantum mechanics. In that case, everyone knows that all eigenstates in such a double-well potential, if it is symmetric, can be classified into symmetric and anti-symmetric, so that the ground state of quantum mechanics is always symmetric, and the first excited states is always anti-symmetric, and they alternate. However, if we consider, at least as a mathematical model, the system where we also take into regard the intrinsic nonlinearity in the two cores, this situation can become completely different when this nonlinearity is strong enough, when, roughly speaking, the strength of the nonlinearity exceeds a particular critical or threshold value. In that case, actually, the ground state of the system may lose its symmetry, and we will observe the effect, which is usually called spontaneous symmetry breaking, due to the interplay of this double core or arrangement with the intrinsic nonlinearity, and eventually we will have the breaking of this natural symmetry, and the ground state will be realized by some asymmetric state. So I will try to give a brief survey of this topic and some results which have been obtained within the framework of this topic. This will be, and the first part of the talk, I will try to focus on some relatively simple, so to say, paradigmatic, in a certain sense, basic models, where this can be studied theoretically in detail, in a rather full form, and then the second part, depending on the time which will be left, will deal with a brief survey of some more sophisticated systems where this spontaneous symmetry breaking effect can be implemented in a more complex form. Okay, so to start with, we can take probably maybe the simplest realization of this dual core system with intrinsic nonlinearity, which can be conveniently formulated in terms of matter waves, in terms of some Bos Einstein condensate. So we can consider a two-dimensional system with coordinates x and y, and we can assume that this is an ultra-cold gas of bosonic atoms, which is trapped in this dual core potential. So we have two parallel potential troughs, which are separated by some potential barrier with the possibility of tunneling across this barrier. So this potential x along axis x, and along y, the system is uniform. There is no potential vector along y. So in this simple setting, we should also assume, to obtain some non-trivial results, we should assume that waves which are trapped in this double waveguide system also have some intrinsic nonlinearity, which is the case both in optics and in BEC. And in BEC, it's the intrinsic nonlinearity is generated by collisions between atoms in this condensate. And if we want to consider the mathematical model, we will naturally arrive at this equation, which is maybe called, if you prefer, the nonlinear Schroedinger equation, or exactly as the case of the application to BEC, it's usually called the Gross-Pitayevsky equation. So this Gross-Pitayevsky equation is two-dimensional, so we assume that somehow we can eliminate the third coordinate. And then what we have here, we have the potential u of x, which is quasi-one-dimensional, as I tried to show in the picture. It's x only along axis x, and along y everything is uniform. And then we have this cubic nonlinear term, which accounts for, in this notation, when we have plus here and also plus here, it accounts for self-focusing effectively, or self-attractive interaction, which in terms of BEC means that the interaction between atoms is attractive, or as people usually say in that case, the scattering length, which determines the interaction of two atoms, is negative. So it's known that in the well-elaborated mean field approximation, the collisions between atoms, the interactions inside BEC will give rise eventually to the addition of this self-attractive cubic term to the simple linear Schrödinger equation borrowed from quantum mechanics for the effective single particle wave function. Okay, this is just the analytical form of that simple potential, which was already shown by means of the picture. Now, as concerns the theoretical analysis of this model, what we would like to find, of course, we should try to find stationary states. So usually is written in this form. We assume that we have a particular eigenvalue of mu. In quantum mechanics, it's simply energy. In the case of BC, it's usually called chemical potential. And then we have some stationary wave function, capital phi, which is a function of x and y. So obviously, this stationary wave function may be assumed real, and it obeys this stationary partial differential equation of the elliptic type, so to say. Now, as concerns physically relevant solutions that can be predicted by the stationary equations, most interesting objects are solitons or localized waves. And so that we would like to find solutions which would be localized both and x and along x and along y. However, the localization in these two directions will have different origin, different explanation. The point is that obviously the localization along x does not need any nonlinearity. It's simply the traditional, the typical quantum mechanical setting with two symmetric potential wells, and of course, just in the one-dimensional situation, we can have the trapped states within the framework of the linear Schroedinger equation. So here, the localization along x is essentially a linear effect. However, along y, no potential is acting, and the localization along y is possible only due to the self-focusing character, self-attractive character of the nonlinearity. So this will be a really solitonic self-trapping along the free coordinate y. So this is a soliton state that we would like to find. Actually, it's not very difficult to find it using this equation. Of course, it's not exactly solvable, but one can easily solve it numerically, and also there are possibility to develop some approximate analytical solutions by means of the variational approximation. In any case, if we are going to find such solutions localized in both directions, the question will be what type of solitons we will have. Before discussing the types of solitons, maybe it's mentioned to briefly, it's worthy to briefly mention something which is written in this transparency. I mean, the model was introduced in terms of the Gross-Petalevsky equation for BEC, but actually exactly the same model can be also interpreted in terms of nonlinear optics. The only formal difference is that in that case, as probably people here know very well, the evolution variable t should be replaced by the propagation distance z. So in that case, actually, this will be a three-dimensional waveguide, a bulk waveguide. Then we can consider the situation in the spatial domain, so there is no time in the optical version of this model. And two parallel potential wells represent in terms of optics the situation where we have this bulk waveguide and two parallel waveguiding slabs are embedded into this bulk waveguide. So this will be the exact optical counterpart of this matter wave problem. Now, proceeding with the consideration of what types of localized states we may expect here, we should ask a natural question about the possible symmetry of the states, because the underlying one-dimensional potential is symmetric. And therefore, it's natural to ask the question, what may be the symmetry of these localized states with respect to the obvious symmetry of the underlying double-well potential trap? So, as I already mentioned, if we have a linear system, let's say just in one dimension, then it's known from elementary quantum mechanics that we would always have either symmetric or anti-symmetric solutions for eigenstates, starting from the symmetric wave function for the ground state. Now, this model that we consider is different from traditional quantum mechanics because in the near-field approximation we also have the nonlinear term. And because of the action of this nonlinearity, the situation may change in the following way. If the nonlinearity remains weak enough, we will still have either symmetric or anti-symmetric bound states, but when the nonlinearity will exceed some critical value, the character of the ground state will change. So the symmetric wave function, which would be the ground state for the wicked nonlinearity, still continues to exist. It will not disappear, but it will become unstable. And so it will cease being the ground state, and the role of the ground state will be actually transferred to a uniform state which appears spontaneously. It will be described by the asymmetric wave function. So how this can be looked at? These are just the examples of such symmetric and anti-symmetric, symmetric and asymmetric bound states which were found exactly in this model. So what is shown here? Here on the right side of the picture, we have the situation still when the nonlinearity is relatively weak. And this picture represents the density distribution in the ground state. So this, the gray stripes represent two parallel potential traps. So this is actually the top view of the system. And when we have the symmetric ground state, we will naturally have two mutually symmetric maxima of the density trapped in these two potential wells. Actually, these two pictures, they show essentially the same situation. The difference is that this is the result of the numerical solution, and this is some crude analytical approximation for the same situation, which was obtained by means of the variational approximation. Although it's not very accurate, but nevertheless it gives the correct idea of the structure of this ground state. Now, this set of pictures on the left side of the slide shows the situation at a much stronger nonlinearity. What will happen here? The symmetric state like this still exists. It did not disappear, but it became unstable. So actually, it's no longer physically relevant. The stable state, which realizes the minimum value of the Hamiltonian, will be the one where spontaneously almost all atoms in terms of BC have been collected in a single potential well. Actually, the second well is not completely empty, it seems to be empty on the scale of the feeder. There is, of course, some non-zero density here, but it's so small that it becomes invisible. And of course, in that case, because this is a spontaneous symmetry breaking, there is no reason that we will always have large density in the upper trough and almost zero density in the bottom trough. It's just maybe the other way around. So there are actually two such states with a spontaneous breaking of the symmetry, which are mirror images to each other. So here's just one of them. And what is shown here is a counterpart of the same symmetry broken state, again obtained not numerically but rather analytically by means of the variational approximation.
May I ask a question?
Sure.
Because of course, your calculation depends on the height of the barrier, right?
Yes, that's right.
And probably you should say, because if we have high enough barrier, but of course then we have states that live on the left and the right.
Yes.
And then the system should fluctuate between two
No, okay. It's not exactly correct. What you said is absolutely correct in linear quantum mechanics. Right. So you will create, for example, the initial wave function, which is concentrated only in one well, but due to the tunneling, it will restore the symmetry eventually. Or you will have some, like Josephson oscillations, right. Dynamical regime. This type of stationary solutions exists due to the presence of the nonlinearity. So in canonical quantum mechanics, this simply does not exist. So if you try to put all atoms into one potential well, even if the potential barrier, which is very tall, nevertheless, due to the tunneling, gradually they will start to oscillate. However, if we have the nonlinearity, this will be a true stationary state, and you will have no oscillations. It will forever remain in this stationary state.
The solitonic states propagate along a y direction, right?
No, they do not propagate along y direction. Okay, this is the x direction, this is the y direction. Well, it may be more natural to use the opposite notation, but anyway, along y direction, we have no action of the potential, everything is uniform, and here it's trapped along y just intrinsically due to the action of the nonlinearity. That it stays exactly in this position and not somewhere here. It's just because here we created it initially, we did not give it any momentum, did not kick it, and because we created it here, it forever stays at this position. If you want, you can put it in motion along y, it's no problem. You just kick it, give it some momentum, and it will start to run.
So the main reason is nonlinearity.
Yes, definitely. The reason for the existence of this configuration as a stationary solution is the presence of the nonlinearity in the Bos equation. Otherwise, if it were the canonical Schroedinger equation, such a solution would not exist. So in that sense, it's not a fundamental solution, because the Bos equation, strictly speaking, is not a fundamental one, it's a mean field approximation. So strictly speaking, you can say that within the framework of the mean field approximation, the Bos equation, this is a true stationary state. Well, if you want to consider the full quantum, many-body quantum theory of the same condensate, and if you wait for millions of years, eventually it will not be a stationary state due to the quantum observations. Okay, now if we want to proceed with the more accurate description of this asymmetric, spontaneously appearing state, we can introduce this natural measure of the asymmetry. So what we can do, we can essentially take the density, and the integral, the double integral of the density will give, of course, the total number of particles in this condensate. And now in the denominator, we simply have the total number of particles. Well, it's actually here is a typo, it should be double integral, but anyway, it's obvious. And in the numerator, we have the difference. We take the difference between the total numbers of atoms which are trapped in the, let's say here, in the right half of the system, minus the total number of atoms which are trapped on the left in the left part of the system. So naturally, this may be used as a measure of the asymmetry. So if the bound state is either symmetric or anti-symmetric, in either case, this will be, of course, 0. But if it is asymmetric, it will not be 0, and this can be used to quantify the effect of the symmetry breaking. Okay, and so this is essentially the most essential result, which is theoretically predicted about the symmetry breaking in this simplest model. So this parameter nu, well, the notation is not the same, but anyway, nu is exactly this symmetry breaking parameter. And it is plotted as a function of n. N, maybe I can come back for a moment. N is simply this total number of atoms by which we normalize the symmetry breaking parameter. Now, we can therefore plot this symmetry breaking, this asymmetry parameter, the strength of the asymmetry, as a function of the total number of atoms. Why it's natural to plot it in this way? Because if the coefficient of nonlinearity was fixed to be 1, therefore essentially this total norm of the solution is by itself the measure of the effective nonlinearity. Naturally, the more atoms we have, the stronger is the average interaction between them. And this is what happens. So if we start the solution from small values of n, this means from the quasi almost linear model, then the ground state will be symmetric, and therefore this parameter is equal to 0. And if we keep increasing the nonlinearity by through the increase of the total number of atoms, we will eventually hit this particular point at which the symmetric ground state will not disappear, it will continue to exist, but the dashed line implies that it will continue to exist as an dynamic and unstable state. So it will lose its character of the ground state. It will continue to exist, but as some unstable state, which is no longer the ground state. Now, what will happen? At somewhat smaller value of this parameter n, or this measure of the nonlinearity, spontaneously at 2 points, they appear new, stable, asymmetric states. They appear, actually this is an example of the phase transition of the first order, when the new state appears not continuously, but some jump. And so at this point where we have the appearance of the new asymmetric states, it appears as a stable one, and it immediately appears having a non-zero value of the asymmetry, and if we keep increasing the total number of atoms, the measure of the asymmetry will be increasing. Actually, here it's, the notation is slightly different. Essentially, if we define the asymmetry parameter as I showed before, it's asymptotic values when all atoms sit essentially in the single half of the system, and the second one is left empty. The asymptotic value will be equal to 1. Here simply the definition is slightly different, therefore it's formally larger than 1. But essentially it will be approaching the asymptotic value, which is equal to 1. And what we have here, we see that there is another branch which also is the asymmetric one, which appears at the same point, but this one goes down, and this one is always unstable. So all this effect exactly represents one of the generic types of the spontaneous symmetry breaking, or another name for this type of the transition between different types of the symmetric and asymmetric states is bifurcation. Well, actually, this is commonly known word here to everyone. And this particular type of the bifurcation is called the subcritical bifurcation, or an alias name is also the backward bifurcation. It's called subcritical because the new symmetry broken state appears subcritically. Subcritically, this means at the value of n, which is slightly smaller than the critical value at which the symmetric state becomes eventually unstable. Or the other name, a backward bifurcation, is that at this critical point we have the emergence of new branches of asymmetric states, but originally, if we track them starting from this critical point, these branches go backward and as unstable one, and they become stable after passing the turning point. For this reason, it's called also the backward bifurcation. Or in terms of traditional condensation metaphysics, it can be also called the phase transition of the first phase transition. So this type of the symmetry breaking is not peculiar just to this particular model, it's sufficiently generic one, and as a matter of fact, this type of the subcritical bifurcation, which gives rise to the spontaneous symmetry breaking, is typical for nonlinear systems in which the intrinsic nonlinearity is self-attractive or self-focusing in terms of optics, because the other situation is also possible where the nonlinearity is self-repulsive. And in that case, the spontaneous symmetry breaking is also possible in a different setting. And in that case, the type of the bifurcation will be different, which we will discuss it soon too. Okay, now these are some just direct dynamical simulations of this two-dimensional Bos-Einstein equation, which simply illustrate how it really works in terms of direct simulations. So what is shown here, in this plot, we take, as you can see, essentially the symmetric wave, as is the distribution of the density. Or not density, of the absolute value of the wave function, but anyway, when we look at the absolute value of the wave function, we see this symmetric state, and this particular plot was generated by simulations when the total number of atoms was relatively low, and therefore the symmetric state was still stable. And there are some oscillations along time, simply because deliberately some initial perturbation was applied to this symmetric state in order to test its stability. So if it's somehow perturbed, you see that it develops some intrinsic oscillations due to this trapped perturbation, but it obviously remains stable. It's not destroyed by this initial perturbation. Now, what we see here, this is a different type of the simulation. Here the simulation started from the stationary state, which was already strongly asymmetric, so it was obtained at a much larger value of the total number of atoms. So practically, you see there is one strong peak on one side of the center of symmetry, and there is no strong peak in the symmetric point. So again, here some initial perturbation was applied to test the stability. It excites some intrinsic vibrations in this bound state, but obviously the bound state is robust. It's not going to be destroyed. And eventually, the third picture shows a situation when the initial configuration is symmetric. You can compare this one and this one. However, deliberately, this symmetric configuration was taken for a much higher value of the total number of atoms, when we know that actually it must be unstable. And here, no perturbation was applied at all initially. All the source of perturbation was just in the truncation errors of the numerical scheme of the simulations. So for a while it remains actually undisturbed because no explicit perturbation was added, but due to the accumulation of small errors of the numerical scheme, which plays the role of some very weak perturbations, eventually this unstable state blows up, and what we see spontaneously is the system forms one high peak of density on one side of the system, here only, let's say, on the left side, and actually we have no symmetric peak on the right side, and then we observe strong oscillation. Because, of course, the system would not immediately jump into a stationary asymmetric states. It develops a strong symmetry breaking, but this symmetry breaking state remains by itself dynamical. It shows strong oscillations, but nevertheless, the dynamical symmetry breaking is quite obvious. Yeah.
The temporal modulation, that all the solutions has the same sort of temporal modulation, is associated to what? I mean, what determines this?
The initial here and here, the initial perturbation was deliberately added.
No, but I mean the evolution in time, it has some maximums and minima.
You mean here?
Yeah.
Well, this is what I said, that you add the perturbations and you this perturbation excites some intrinsic oscillations in the system.
So this is relaxing so at the end.
It's not relaxing to, well, it may be relaxing, but very, very slowly. The point is that the system is conservative, so there is no dissipative mechanism of relaxation. In principle, there is a mechanism of relaxation. Is the direction of why the system may emit radiation. And so this may be some effective mechanism of relaxation, but because the system is conservative, this mechanism is extremely weak. So if you extend this simulation maybe by 2 orders of, for the time by 2 orders of magnitude longer, maybe eventually you will see some gradual decay of the oscillations. But essentially here you see simple oscillations.
And the frequency has to do with the equivariant solution. But then when you go to the asymmetric, so these high peaks,
yes.
That frequency, what is determined?
Its frequency principle is determined by the dynamics of the system, but the point is not easy to answer the question because these are not small perturbations, there's a large perturbation. Yeah. So somehow they are defined by the entire nonlinear dynamics of the system, but it's not possible to explain it in simple terms. Once again, the situation is like this. We know in advance that this stationary state is definitely unstable, and even a very small perturbation eventually gives rise to its blow-up. And this blow-up somehow generates this large amplitude oscillations. Okay. Now, so this was one generic case of the intrinsic attractive nonlinearity. Now, it may be physically relevant to consider also the case of a similar model but with the opposite sign of the nonlinearity, which would be self-repulsive. In BEC, actually, the self-repulsive nonlinearity is most typical. Self-attractive nonlinearity is also possible in BEC. It can be induced through the particular physical mechanism which is called Feshbach resonance, essentially by placing the condensate into external magnetic field, but it's a relatively exotic situation. However, in optics, as you know, the most typical nonlinearity is self-focusing, is a classical Kerr effect. And the negative Kerr effect may occur, for example, in semiconductor materials, but it's something more exotic. In any case, it makes sense to consider what will happen in terms of the symmetry breaking effect when we have the self-repulsive or self-defocusing nonlinearity. And this can be analyzed usually there is a similar model. So what we do now, we take almost the same system. So as I said, now we are going to switch the sign of the nonlinearity to the opposite. But it's not enough. We should also make some other changes in the system. When we had self-attraction, the system was simply uniform along y. Now, if we have the self-repulsion and uniformity along y, or if in terms of BEC, all atoms will simply escape along this free direction. We will have nothing. What is necessary to do? In addition to this double well potential we have in the same form as before, we should also add some potential acting along y. However, we don't need to make a trap like we had here. It's not necessary. It's enough to apply some potential which will be simply periodic along y. As you know, of course, from quantum mechanics, if you have linear quantum mechanics and simply the periodic potentials, there is a Bloch theorem and there are no localized wave functions, stationary wave functions. You may only have quasi-periodic Bloch wave functions. However, it's not going to be necessarily true in our case because we also have the nonlinearity, and in the case of the nonlinearity, there is no Bloch theorem, as a matter of fact. Okay, so this is what we are going to consider, this type of the setting with self-repulsive nonlinearity, maybe self-attractive too, actually with both sides of the nonlinearity. And now we can once again write the model. So this is again the Gross-Petayevsky equation. Now I put here the sign parameter sigma. If it will, in this notation, if it is +1, it will be the self-repulsion. If it is -1, it will still be self-attraction. U of x is exactly the same potential that we had before. Now we add this, as I said already in words, we add additionally the periodic potential which acts along y. And the question that we would like to ask is, if in this model, generally speaking with a self-repulsive nonlinearity, we may first of all have some localized states, so essentially a soliton, and then if we can predict some symmetry-breaking effect for that soliton. First of all, the soliton is possible. And the naive question would be, how can it be? Because we have the self-repulsion of the field, and even when we have no self-repulsion, just the periodic potential, we have the Bloch theorem, and all wave functions should be delocalized along y. And when we add the self-repulsion, it's naively speaking, it seems that we should make the wave functions already still more self-delocalized. Naively speaking, this is correct. However, what happens is the following effect. If we look at the linearized version of the system, and we will have some, the so-called band gap spectrum along y, generated by this periodic potential, like simply as a Messier equation. Yeah? And so, as you know, this periodic potential, it gives rise to the band gap spectrum when we have bands where delocalized Bloch waves can exist, and at some other values of the energy, there are forbidden gaps where Bloch waves do not exist, and in the linear equations there are no solutions with chemical potential or energy falling into this forbidden gap. Now, what may happen when we have the nonlinearity? New solutions appear exactly inside this forbidden gap. And roughly speaking, and this new solution will be exactly a soliton. As a so-called gap soliton because it lives in terms of its spectral properties inside the form of forbidden gap. Why it can exist there? A very crude approximation can be given as this. We can look once again at the band gap spectrum of the linearized system, and we can look at the effective mass of the collective excitation in the presence, which can propagate in the system in the presence of this periodic potential. So the known fact is that this collective excitation may have both positive mass and negative mass. So in some regions of the spectrum, the effective mass of the collective excitation can be negative. And now what will happen is that the interplay of this effective negative mass with the self-repulsive nonlinearity will give the same effect as the interplay of the normal positive mass with the self-attractive nonlinearity. In either case, minus is so in the former case, minus times minus will give us still plus, and therefore the soliton is also possible in the case of the self-repulsive nonlinearity when it interacts with the periodic potential. This is what is called the gap soliton. Once again, it's not what is called the dark soliton, it's a bright soliton, but with a more complex structure. Okay, now if we have the gap soliton, now we should look at the fact that we also have the coordinate x. Along x, we still have this natural symmetric double structure of the potential, and therefore we can ask the question: what will be the symmetry of the gap soliton with respect to this additional coordinate x? And obviously, we may have symmetric or anti-symmetric gap solitons before we are going to consider more sophisticated possibilities. Okay, and then the question is that if we keep increasing nonlinearity, maybe some bifurcation will occur to symmetric or anti-symmetric gap soliton modes. And this is indeed what happens. However, it happens not in the same way as we discussed in the case of the self-attraction. In the case of the self-attraction, as I said, the bifurcation would break the symmetry of the symmetric state. Actually, anti-symmetric states also exist in the attractive system. But in this model, virtually all the antisymmetric states, so they suffer no bifurcation, nothing happens to them, but from the very beginning, actually, they are completely, they are almost completely unstable. Because they are unstable from the very beginning, they are not very interesting. Now, here the situation is different. In the case of the repulsion, we can have gap solitons of two types, symmetric and antisymmetric. Symmetric solitons will be generally stable in the case of the symmetric gap solitons, and antisymmetric gap solitons may also be stable. But then this symmetry-breaking bifurcation will never happen to symmetric states. So if they exist as symmetric states, they will keep existing as symmetric states with the increase of the nonlinearity. Nothing will happen. However, this time, the bifurcation will happen to antisymmetric states. Before showing that, maybe we can briefly look at the situation which still corresponds to sigma equal to -1, which means we still have the, for the time being, in this slide, we have still the self-attracting nonlinearity. And this is what happens as we gradually increase the strength of this additional periodic potential, starting from 0 up to some particular value. We still have the symmetry-breaking bifurcation of the symmetric states, but the character of the bifurcation is now modified. Originally, we still have this subcritical bifurcation, and as we increase rho, gradually we have the change in the shape of this bifurcation curve, and eventually we will have the switch from the subcritical bifurcation to the simpler supercritical bifurcation, when the new asymmetric solutions appear immediately at the critical point, they immediately go forward, and they are immediately stable, as a matter of fact. So, roughly speaking, the phase transition of the first kind will turn into the first transition of the second kind. Okay, but now let us look at what will happen in the case which is sort of new, when we have the antisymmetric, self-defocusing nonlinearity. In this case, as I said, nothing will happen to symmetric grounds, symmetric gap solitons, but something will happen to antisymmetric solitons. So we may call this, strictly speaking, antisymmetry-breaking bifurcation. But in terms of the density, the description will be the same. We can use the same definition of the symmetry-breaking parameter because it's sensitive only to the density, not to the sign of the wave function. And so here we have a set of such bifurcation diagrams for different strengths of this periodic potential. If the periodic potential is absent, we simply don't have gap solitons at all. So it must be always present. And here the generic feature is when the bifurcation is generated in antisymmetric states under the action of the self-defocusing nonlinearity, it is always the supercritical bifurcation, or in other terms, it's always a phase transition of the second kind. So when we attain this particular value of the nonlinearity, where the antisymmetric state will lose its stability, it will immediately give rise to the pair of new asymmetric or antisymmetry broken states, which go forward as stable solutions. And so this is a principal difference between, depending on the sign of the nonlinearity. The self-attractive nonlinearity typically gives rise to the subcritical bifurcation of the symmetric states, and the self-repulsive nonlinearity typically, not typically, but always actually, gives rise to the symmetry, to the supercritical symmetry breaking of antisymmetric states. So this is the generic property. Now we can consider some generalizations and variations of this. For instance, one possibility is we started the analysis of the model using the two-dimensional Boris-Potayevsky equation. But we can simplify it in a certain sense. We can say, let's assume that each potential well is very deep, and the trapping of the stuff in that well is quite strong. So the linear coupling because of tunneling is weak. In that case, we can naturally approximate this two-dimensional Boris-Potayevsky equation by a system of two one-dimensional equations. So we can introduce two wave functions psi and phi, each is just one-dimensional, and it describes this condensate which is trapped separately in one of these potential troughs. So generally, we also introduce this periodic potential. I'm sorry, because actually what was y in the previous part of the talk now became x, but anyway, it's the same potential. We can consider both signs of the nonlinearity, self-attractive or self-repulsive. And then we say, because now we have the one-dimensional description and two one-dimensional wave functions, we should explicitly introduce this linear coupling term, which takes into regard the possibility of the linear coupling, so linear mixing essentially, between two one-dimensional wave functions psi and phi. So this is sort of a simplified description of the previous model, which admits actually a more straightforward analysis. Okay, and so what happens in this case is that, again, we can predict a similar phenomena concerning the symmetry breaking. For example, this is here we take the situation with the self-repulsion when I'm sorry, this is the picture which illustrates self-attraction. Self-attraction, we start from the symmetric soliton. Here, just for convenience, both wave functions are juxtaposed. They're shown together in a single plot, but actually these are two different wave functions. So we start from the symmetric stationary solution, and it spontaneously develops this instability just due to the intrinsic numerical noise in the simulations. And so we see that spontaneously the system prefers to have a bigger number of atoms in one potential trap and a smaller number of atoms in the other one. Of course, because we don't, this is a conservative system, it cannot immediately relax into a stationary state. It also keeps demonstrating some oscillations. But this is a very typical situation of the spontaneous symmetry breaking. Okay, another thing, so this is, we can take the same system and produce the general stability diagram to show different types of stable solution which can be found here eventually. So this is the strength of the linear coupling between the two traps. And this is the strength of this periodic potential which acts along the form of free direction. So what happens is that when the coupling is very strong, we have only the symmetric, the only stable state is the symmetric one due to the strong linear coupling. Then this is the line of the bifurcations of the symmetry breaking. Below this line, the symmetric state became unstable, and we have developed the stable asymmetric state. And only this one it represents a stable situation in this model, in this parameter region. And eventually, at still smaller values of kappa, what happens, the antisymmetric states, which do not suffer any bifurcations, they just remain antisymmetric, they can be stabilized. They also exist here, but they're always unstable. Beneath this line, the antisymmetric states can, for some different mechanism, they can actually enjoy stabilization, and therefore here we have the bistability. Because simultaneously, the asymmetric states are stable and antisymmetric states are also stable. Okay, now another generalization. Thus far we were talking about simplest fundamental soliton, which roughly speaking, if you look along X, it was a soliton with a single peak. But the same, due to the presence of the periodic potential, the same model supports also high order solitons. For example, we can easily find this odd soliton or twisted soliton or dipole soliton, which is antisymmetric but in a different sense. It's antisymmetric not because we have different signs of the two components, but simply it's spatially antisymmetric. And so this odd mode, the spatial antisymmetric mode, simultaneously may be asymmetric with respect to the two components. So you see here we have the plots of the wave function of two components. Both are odd or twisted spatially, however they have different amplitudes. And this is a direct example of the spontaneous breaking of the symmetry of higher order solitons. And one more simplification, we can take essentially the same model and now drop the periodic potential. So we can take a system of two coupled one-dimensional equations. We still keep, of course, the linear coupling, the linear mixing, but now we drop the periodic potential. And we also change the notation. The evolution variable will be z, and for the former coordinate will be called tau. What we will arrive at, this is a standard model of what is called the dual-core optical fiber. Completely different physical system, but nevertheless, as a model, it's closely related to the previous one. And so this is a standard nonlinear optical fiber with the intrinsic Kerr effect. The sign plus here implies that this is anomalous group velocity dispersion. And the difference from the simplest model of the optical fiber is that we assume the dual core fiber, and we assume that there is linear mixing of the weight of the light in the two cores. So U and V are amplitudes of the electromagnetic field propagating in the two cores. So and in this model actually is the first one where the spontaneous symmetry breaking of solitons was predicted approximately more than 20 years ago. Actually, it was first predicted in several works, starting in 1990, and it was predicted analytically by means of the variational approximation and also tested numerically. And here, the typical bifurcation diagram, maybe I will skip this. This is a typical bifurcation diagram. This is some measure, it doesn't matter how it's denoted, it's a measure of the symmetry breaking. This parameter is a total energy of the soliton, essentially the same which used to be the total norm, the number of vectors in the case of BC. So it measures the strength of the self-attractive nonlinearity. So up to this critical value, the symmetric soliton as a dual cofiber remains stable. Here it becomes unstable, and here we have the slightly subcritical bifurcation, which switches the system into the asymmetric state. So this actually is exactly this diagram is the first, historically the first one, which predicted the spontaneous symmetry breaking in solitons. Okay, now we have some 5 or 10 minutes. I will give a brief overview of more sophisticated systems where similar symmetry breaking effects were predicted, but in slightly different settings. So this is a more sophisticated model, obviously. It's a model of 4 equations. What it essentially describes, it describes again dual core fiber. However, this is a dual core fiber with the additional intrinsic structure with the Bragg rating. So what we have 2 parallel cores. Each core is a nonlinear optical fiber. There is linear coupling of light across this gap which separates the 2 cores. So the ingredient or the feature which we already discussed. A new feature is that we assume that this system of weak local defects is written on the surface of each fiber, and the periodicity of the system of defects is half of the wavelengths of light which propagates in the fibers. So this is exactly what is called the fiber Bragg rating. And now we have, in principle, the system for 4 waves, because due to the resonant Bragg reflection, we have both right and left propagating waves inside each core, and then we also have the linear mixing between waves which can propagate in different cores, because light may couple from one core into the other. As a result of all this, we can derive the system of 4 equations. This is a so-called system of 4 coupled mode equations, which is the simplest situation, describes this dual core fiber Bragg rating. And here also we can predict symmetry breaking of solitons, and this is a typical bifurcation diagram. So lambda is here the coefficient of the coupling between the 2 cores, and omega is the intrinsic frequency of the soliton. Okay, so here we have a whole set of bifurcation diagrams, and it shows how it changes the shape of the bifurcation diagram within the total family of many solutions that we may have here. Okay, now this is an illustration of the direct simulation of the model. Here we start from the symmetric soliton, juxtaposing 2 components. When they're unstable, and we see that spontaneously indeed one component starts to grow, the other starts to decay. On the other hand, if we can find this already stable asymmetric state, and it remains really stable in the course of the evolution. Okay, and then another generalization. I already mentioned that we could approximate the original 2-dimensional Gauss-Petayevsky equation by the system of linearly coupled 1-dimensional equations. Now what we can do, each of those equations itself we can make 2-dimensional, which means the following. We have now the 3-dimensional space. In the 3-dimensional space we have 2 pancakes. Each pancake is a trap for the Bos Einstein condensate, and we have the tunneling in the vertical direction across the gap which separates 2 parallel pancakes. And inside the pancake, we have the 2-dimensional Gauss-Petayevsky equation with x and y, and additionally, we have the linear coupling between them. Here again, we can start from the 2-dimensional solitons and analyze various symmetry-breaking effects. For instance, this is a case when the intrinsic nonlinearity is self-impulsive. Then we may have the anti-symmetric gap soliton, two-dimensional gap soliton, and this is a result of its symmetry breaking. We juxtapose two different components in one plot to show that we have the stationary solution, which is stable by itself, in which the amplitude of one part is one component is essentially higher than the amplitude of the other two-dimensional component. This is a result of the symmetry breaking in this two-component, two-dimensional soliton. And also similar, still more sophisticated result can be found when we establish a fundamental two-dimensional soliton. We may take the vortex. It does not seem as very much as a vortex, but actually it is. It is a multi-peak soliton with some circulation of the phase between along this chain of peaks, so that the total circulation of the phase in this case will be 4 pi, which means that each complex carries a topological charge 2, vorticity 2 in other words. And these two-component, two-dimensional vortex solitons may also suffer the symmetry breaking and develop this particular stable structure when we have a large amplitude of the vortex in one pancake and a much smaller amplitude in the other. This is a result of the symmetry breaking between vortices. So it's also possible. Okay, and then still another generalization. We can come back to the optical models. In optics, we have not only the kernel linearity, but we may have in some crystalline substances, we may have the second harmonic generation, which means we will have the quadratic nonlinearity. So the quadratic nonlinearity is a well-known physical effect, which is described by this type of the nonlinearity. So roughly speaking, the square of the fundamental harmonic generates the amplitude of the second harmonic. What happens here? And now we may have we may take two copies of such standard models and assume that we have two parallel waveguides where we have the second harmonic generation and the linear coupling between them. So so here we can analyze the symmetry breaking with these solitons with the quadratic nonlinearity. This is some set of bifurcation diagrams. Just one thing to say about them, that in that case of the quadratic nonlinearity, the type of the bifurcation is supercritical. Okay, now still another interesting remark. I mentioned, and I'm trying to stress, that there is the most fundamental effect found in all this theoretical analysis is, once again, when we have the self-attractive nonlinearity, which is accounted for by this cubic term, we are going to have the subcritical bifurcation, which destabilizes symmetric solitons. On the other hand, if we have the self-defocusing nonlinearity, which may be accounted for by this term with opposite sign, we will have the trend to the supercritical bifurcation, destabilizing antisymmetric states. Now we may have the model where we put both nonlinearities together, the so-called competing nonlinearities, or the cubic quintic model. The cubic nonlinearity is self-focusing, simultaneously the quintic nonlinearity is self-defocusing. We assume the system has two cores. These competing nonlinearities act separately inside each core, and we have the linear coupling between them. What will happen? The answer is that we will have the bifurcation diagram, but now, because of this competition, the bifurcation diagram will develop the shape of the loop. So we increase the total norm, so the strength of the nonlinearity. Here, for example, we have some supercritical bifurcation, but then we will have the inverse bifurcation, because at very large values of nonlinearity, this self-defocusing quintic nonlinearity will be dominating. Of course, it will try to restore the symmetry of the symmetric state. And therefore, we will have this loop formed by the in the form of the bifurcation diagram. So we have actually a set of two different bifurcations. And now what we can do, we can just monitor the change of the shape of this loop as we keep increasing the coefficient of the linear coupling between the two cores. So this loop shrinks gradually, and if we keep increasing this coupling constant, eventually we will have a very small loop like this, and eventually it will collapse and disappear. So when the coupling is too strong, no bifurcation will happen at all. We will always have just the stable symmetric soliton, nothing else. Okay, and then the last thing. All the models that we discussed briefly, they were models of the conservative type. Symmetry breaking is also possible in dissipative systems. So what we can take as the simplest model is a system of two one-dimensional Ginzburg-Landau equations. They are written in terms of the optical notation, like for something like for laser cavity, roughly speaking, with a cubic quintic nonlinearity. So this is we have the complex coefficient. Generally speaking, we have the complex coefficient in front of the quintic term, right? And we have also the cubic nonlinearity here. And then we postulate that we have such two parallel Ginzburg-Landau equations, and we have the linear coupling between them, as before, to investigate the possibility of asymmetry breaking. Now, it's well known that the cubic quintic Ginzburg-Landau equation by itself may give rise to the dissipative soliton. And now the natural question would be to consider the possibility of the symmetry breaking in the two-component dissipative soliton, which is possible too, and the results can be formulated in the form of this not bifurcation diagram, but diagram of different phase diagram of different states. And so there is actually, as you see, a large area which is occupied by stable asymmetric dissipative solitons, which are exactly produced by the symmetry breaking of the obviously existing symmetric dissipative soliton. Okay, well, still a couple of words. All the previous analysis was done for continuous models. For the discrete models, it's also possible to consider. We can take this type of effects. We can take two discrete nonlinear Schroedinger equations. It's actually a discrete version of the model that we considered before. The difference is that now instead of the continuous NLS equation, we have the discrete equation, and again the linear coupling between these two discrete subsystems. So now we will be dealing with discrete solitons. The discrete solitons, due to the linear coupling, they will also give rise to the symmetry breaking. In the case of the self-attraction, the bifurcation diagram will be subcritical, as we should expect in the case of the self-attractive nonlinearity. Or this is another version when we have also two linearly coupled discrete subsystems, but this time we assume that the linear coupling is applied just at a single side of this discrete system. The difference will be that in this case, the symmetry breaking also happens, but the bifurcation diagram will be supercritical. This is the equations for the latter model. And this is the example of this supercritical bifurcation when we have these discrete chains which are coupled linearly at a single site. Okay, now we can proceed to the conclusions. So the conclusions are relatively simple, although there are many different examples, many particular results, but general conclusions are still can be formulated and they are not very complex. So as a result of the competition in dual core systems between the intrinsic nonlinearity acting inside each core and effectively linear coupling between the cores, we may have effects of the spontaneous symmetry breaking of solitons, not necessarily solitons, but here we consider solitons. And the generic features of this symmetry breaking phenomenology can be stated so that when we have the action of the self-focusing nonlinearity, it gives rise to the symmetry breaking of symmetric solitons, and typically the corresponding bifurcation is subcritical, or in other words, the corresponding phase transition is a phase transition of the first kind. On the other hand, we also have gap solitons in the case of the self-defocusing nonlinearity. In that case, the symmetry breaking happens to anti-symmetric solitons, so this is an anti-symmetry breaking bifurcation, strictly speaking. And its most salient feature is that it will be always the bifurcation of the supercritical type, or in terms of the phase transition, it will be the phase transition of the second kind. Okay, and then these conclusions, which were first obtained in the simplest model, roughly speaking, of two coupled nonlinear Schroedinger equations, then can be extended in many different directions. So they were analyzed theoretically for dual Hobre gratings, and they could be extended to discrete lattices and also to dissipative models when we have linearly coupled systems of complex Ginzburg-Landau equation. And so the real challenge to be added as a final conclusion is to observe the symmetry breaking effects in solitons experimentally. In the real experiment, symmetry breaking was observed both in matter waves, in BC, and in nonlinear optics, but thus far, at least as far as I know, It has never been observed in solitons. It was observed in something which may be called a continuous wave, CW. So that it was a nonlinear effect, but the underlying state, whose symmetry was spontaneously broken, itself was not a soliton. It was just a uniform state. And so to do something experimentally for the solitons remain, I think, a true challenge. Okay, muchas gracias.
So, we have questions on question.
You have given a very large number of examples of symmetry-breaking by nonlinear effects. Now, is there any general statement that you can make? You have tried in your conclusion. Is something that can be proved as a general result for nonlinear symmetry-breaking, or what is the minimal model that would show whatever you want to?
Yes, the minimum model was actually demonstrated. Maybe we can come back briefly to the minimum model. It's also historically the first model where this was considered, and it's really minimal one. Okay, this is the minimal model. So you have two nonlinear Schrodinger equations with a linear coupling. If you drop the linear coupling, it will be integrable equation with commonly known solutions for stable solitons. Now you introduce a linear coupling. The model is no longer integrable, and this is the simplest setting which allows you to study symmetry breaking in solitons. And this was historically the first thing which was done. Approximately, the first results were reported in 1990, 21 years ago.
So in this talk you have presented symmetry breaking for stationary states.
Yes.
I guess mainly. Do you know, or have you considered, or somebody else has considered symmetry breaking with oscillatory solutions?
In principle, yes. Actually, indirectly, you could see in some plots here. Maybe I will quickly try to find some particular examples. Okay, so actually, no, I should go back probably. Not forward. Okay, here, something like this. So here it was still the example of the dynamical simulation which shows you the symmetry breaking of the stationary state. But slightly modifying this simulation, you can explicitly study, if you want, the symmetry breaking of oscillatory state. So essentially what you see here, this is a symmetry broken oscillatory state. With persistent internal oscillations of each component of the soliton, and they are not going to decay, these oscillations. So this is, as a matter of fact, indirectly speaking, an answer to your question.
Yeah, but so they say, if they are in phase or out of phase in the oscillation, or they have symmetric or asymmetric in the amplitude?
If they are in phase or out of phase here, they are not quite regular oscillations, so it's hard to say. But I would say this can be studied, and most typically these oscillations, if you follow accurately the oscillations of components in the two traps, they will be out of phase. Is a clean form, so to say.
In order to understand the nature of the symmetry breaking, you have modified, for example, the potential or the nonlinearity. What you left constant is always the geometry
Yes.
of your waveguide.
Yes.
What would you, for example, did you have a look at if you had not two waveguides but a triangle or three waveguides?
Yes, this was studied, not in full detail, but this was done indeed. There were some, I am aware, I can immediately offhand recollect two examples of such triangular systems. Actually, wasn't three even. Well, one thing is that just last year there was a paper of some people from Belgium, I guess. What they studied, a very simple model. They assumed that you have exactly these three potential wells, and they approximated them simply by three ordinary differential equations. So there were no solitons, just 3 degrees of freedom. And they postulated symmetric couplings between adjacent wells. And just analyzing this as a dynamical system with 3 degrees of freedom, they were able to find various symmetric and symmetry broken dynamical states, actually fixed points, stationary solutions in the system. So this is maybe the simplest example. But also some more sophisticated things were done. In particular, something like 7 years ago, I had a paper with my former student, Gubeski, the same guy with whom he mentioned, for example, he produced this picture. So what we considered with Gubeski in another work, which I didn't include, it was like the system of 3 parallel break gratings, which also in the cross section they also would feature the equilateral triangle. In that case, well, here I briefly mentioned the symmetry breaking of the two-component soliton, but in the same way, not the same way, but similarly, you can study the symmetry breaking of the three-component soliton. This was done, for example. And then, still for the dissipative solitons, there was at least one work with Dmitry Scriabin, my other former student, Ariel Ziegler, and myself. We had a paper in PhysRef A maybe 4 years ago, where we can see that the system of coupled cubic indivisible Landau equations, not 2 but 3. It's a straightforward generalization for the threefold symmetry, and we analyzed what kind of dissipative solitons you may have in that case. So in some settings this was done.
I have a question. Many of your systems were conservative, but you also at the end took the case of the dissipative systems. I'm more familiar with the dissipative one, so I'm going to pose the question in that context. In those systems, when you have sole localized solutions, you also have extended patterns. And usually the extended patterns coexist with the continuous solutions plus the solitons and so on. The question would be, is anything on the properties of the breaking of the symmetry that arises in the solitons where there is asymmetric or symmetric solution that appears, that can be also inferred or could be extended to the case of the pattern, so that if a sort of asymmetric solution takes part in that case would also be the same for the pattern or whatever. Is any?
Yeah, okay. In principle, yes. If we have symmetry breaking of solitons, in a more actually in a more simple situation, in a sense, we may also have the symmetry breaking of extended states. There is some systematic difference, and this difference can be the easiest way it can be illustrated if you just come to the simplest model or in all this business. The simplest model is this one. So what we can do here in this model, one can drop these dispersion terms completely. And so, formally speaking, we can reduce the system from the coupled partial differential equations to coupled ordinary differential equations. Although the system will look extremely simple, then you, of course, you will have still stationary solutions when U is simply a function of Z without any tau dependence. This is what is usually called CW, or continuous wave. Was the simplest example of the extended state. If you drop this term, you don't have the modulation stability, therefore it's a physically relevant situation. So the symmetry breaking of such CW, as a matter of fact, within the framework of this model, was studied before the symmetry breaking was studied in solitons. For the first time in this type of the model, it was studied not in relation to optical fibers, in more abstract context. Maybe in 1986, there was a paper by Scott, Ilbeck, and someone else, I at this moment don't remember the third name. And what these people did in the framework of this simplified model, they demonstrated that you may have symmetry breaking. The difference of the symmetry breaking in the CW state from the symmetry breaking of solitons is in the character of the bifurcation. For solitons, as I tried to stress, the bifurcation is subcritical, at least slightly, weakly subcritical. For the CW states, it is always supercritical.
But the fact that the bifurcation is quite safe. Also, another question related to this. If I think on two waves which were different directions of polarization or light, this would be by refringence coupling. There will be another coupling which will be on this term.
Yes,
which will be
XPM.
Yes, which this will come through the material or whatever the background material.
Yes.
You always consider the sort of by refringence.
Yes, that's right.
The other term, which it has a more symmetric component, because this clearly like many of the symmetry would help in having more symmetric solutions.
Okay, good question. Actually, this model, when you also include, at least formally, you also include the nonlinear coupling between the two waves. Exactly what you said, this may be a single core of the optical fiber, but for two orthogonal polarizations of light. This model was studied, as far as I know, in a relatively consistent way, only very recently. Actually, just in the beginning of this year, we had a paper with my Japanese collaborators, Hidatsugu Sakaguchi, where I guess we considered it for the first time in a sort of consistent way, develop sort of a consistent analysis. And we studied how this bifurcation will be modified exactly when you add the XPM coupling. Well, I cannot, it's not easy to answer immediately if the XPM coupling will help to suppress the symmetry breaking instability or will enhance it. Rather speaking, different things may happen. The system becomes rather complex, but nevertheless it can be analyzed.
Thank you. Any more questions? Sorry, thank you.